let us take stock. We are interested in computing the probability of a success run of length 5 on or before the nth trial, Sn. We managed to reduce that to a question about the probabilities of first success runs, F1, F2, F3 through Fn. And we managed to fob that off to a question about computing the probability of any success run terminating at a given point, say n. If I can compute un for any n, then I can compute the f's. This looks even harder. But an appeal to additivity, just one more time, third time pays for all, will settle it for us. And at the heart of this excursus of additivity is a key appeal once more to the fact that we're dealing with independent trials. Let's take a close look at what happens if we have successes in the 5 trials terminating at trial n. If we have successes at trials n-4, n-3, n-2, n-1, and n, if we have 5 successive consecutive successes, then it must be the case that in one of those 5 locations there must be a success run which has terminated. A picture is worth 1,000 words here. So let's draw the possibilities. Imagine a setting where from trials n-4 through n we have a string of 5 consecutive successes, 5 ones. And let's focus on that. Now, if this is the case, then the first row of the picture shows you one possibility, that yes, you had 5 successes there, and it transpires that a success run of length 5 terminates at the nth trial. How could this happen? Well, you could have a failure at trial n-5. If that happened, then you have a success run terminating at trial n. Or this could be a string of 2 consecutive success runs. So you have one success run terminating at n-5, and then another success run immediately afterwards terminating at n. Or it could be a string of 3 consecutive success runs terminating at n. All these cases are folded into the first row on your table. And the probability of that, by fiat, by convention, is what we call U sub n. The probability that there is a success run, first or subsequent, terminating at trial n. Here's one way in which you could get 5 ones in a row from trials n-4 through trial n. Another possibility is that a success run terminated at trial n-1, meaning that you must have successes from n-5 through n-1, followed by one more success, which may or may not be the start of one more success run. Here's another way of getting 5 ones in a row. To get a success run which terminates at trial n-1, it must be the case that either there was a failure at trial n-6 immediately preceding it, or it was one of 2 consecutive success runs, or one of 3 consecutive success runs, and so on. All of these possibilities are captured in our notation in un-1. And so we have a success run terminating at trial n-1, probabilities un-1, and a success to follow, shown in maroon, and that gives you a probability 1/2. Independent trials means these 2 probabilities must multiply. The next possibility, the third row on the table, says that now we have a success run terminating at trial n-2, followed by 2 successes, which may or may not be the start of yet another success run. And then another possibility, where you have a success run terminating at trial n-3, and finally a success run terminating at n-4. And a little introspection convinces us that if we have 5 ones in a row from trials n-4 through trial n, then one of these 5 possibilities must transpire. There must be a success run terminating somewhere in that string of 5. And now additivity puts everything together. The probability of 5 ones in a row from trials n-4 through trial n is 1/2 times 1/2 times 1/2 times 1/2 times 1/2, or 2 to the -5. This is because the trials are repeated and independent, and the coin is fair. And now we stitch together the possibilities. The first row has got probability un. A success run terminated at trial n, in which case you do get 5 ones in a row. Or a success run terminates at trial n minus 1, probability un minus 1, and you have one more success, which is un minus 1 times 1/2. Or a success run terminates at trial n minus 2, probability is un minus 2, and then you have 2 successive successes, and the probability of that is 2 to the power minus 2. And we systematically stitch the pieces together. And these 5 pieces added together must give you the probability of the event that you had 5 ones in a row. Oh, this is lovely. I should mention that up to this point, our development had been generic. We could have replaced coin tosses by other experiments where there were renewals. And our arguments would have been essentially the same. But this is the first place where the essential nature of the coin toss and the fact that we are looking at sequences of successes, runs, comes into play. Right? So here's where we are using problem-specific information as opposed to more generic analysis. At the end of the day, I've got an equation which has taken up a certain amount of real estate. It looks a little complex. What do we learn from it? And let's keep our eyes firmly on the prize here. What's the key thing we want to look at? We want to say something about un, the probability that there is a success run, first or subsequent, at trial n. Isolate un on the right-hand side and move everything to the other side. And now we've got a new expression, un in terms of other things. But a little look at the right-hand side tells us that we are primed for yet one more slogan. If I know the first n minus 1 values, u1 through un minus 1, then I've got a pathway to deducing the nth value, un. Oh, this is very pretty, because this says if I know u1, I can construct u2. If I know u1 and u2, I can construct u3. If I know u1, u2, and u3, I can construct u4, and so on down. Here's a recursive pathway to computing the probabilities un. Now everything is in place. Now let's assemble and put everything together.